Welcome, Professor Bright here. We're going to look at complex eigenvalues, eigenvectors, and stability this week. Before we begin, though, we probably want to do a little bit of review of complex numbers. So I have some expressions here. I just want you to review them, and you might need to pause the video, look things up, kind of rules with complex numbers, but go ahead and complete these. And here are the answers. So the bar over the top just means the conjugate, and that means change the sign in front of the imaginary component. When we divide complex numbers, we actually multiply by the reciprocal, or multiply by the complex conjugate to numerator and denominator. And then the last one, just remember that I times I is minus 1. Okay, so some more review related to complex numbers. Here we go. They come in pairs. Okay, so z and z bar. We call the z bar the complex conjugate. Okay, so just so we're all clear with the language, conjugate. Okay, and we can plot these in the complex plane. So when we do this, we always plot the horizontal axis as the real component of z, if we call this z, and then the vertical axis would be the imaginary part. Okay, so for example, 3 plus 2i, we can go over 3 and up 2, and boom, there we are. Okay, we can also express them using polar coordinates. Okay, so if we have, a point here, which is z, which is equal to a plus bi, right? And so that's a complex number, and then we would say, okay, well, we have a line connecting from the point to the origin, right? And the length of this line segment, you might imagine we call that r, because that's polar coordinates, and so we say that distance is r, and we call that the modulus of z, and to compute it formally, we just do square root of a squared plus b squared, square root of all that. Okay, okay, and then if you remember from polar coordinates, you also just have to discuss an angle theta, and that is the angle from the positive, or from the real axis, so that's going to be theta. Okay, and so we call theta the argument of z. And we can find it in a variety of ways. We can say that the most common one is to say that theta is tangent inverse of b over a, because again, you have a component here which is b, and that's a. Just kidding, a and b. And so then you do tangent inverse and you're done. Okay. Consequently, because of all this, we can acknowledge that the transformation from the complex plane to using real or polar coordinates, we can find that a is r cosine theta, b is r sine theta, and then z we can express as r, and then cosine theta plus I sine theta. And you might have seen the notation before. This z is equal to r cis of theta. It's a common abbreviation, so just be aware of that. Okay, and then also with complex numbers, we get a couple nice theorems. Okay, so there's de Moivre's theorem, and you can look this up if you want, but this tells you, formally, I think of it as the way to get the nth roots of unity, but in any case, z to the power of n, so a complex number raised to a power of n, we can compute that by taking, well, we know that this is r, and then cosine theta plus I sine theta, as we just discussed, right? And then we would do all that to the nth power, and according to de Moivre, that is the same as r to the n, and then cosine of, parentheses, n theta plus I sine of n theta, or put more succinctly, this is r to the n cis of n theta. Okay? And then the last theorem that we have, and you've likely seen this before, is e to the I theta, and we might know that e to the I pi is -1, but to get that, we can say that this is a result of Euler's formula. E to the I theta is equal to cosine theta plus I sine theta, which is used in de Moivre's. So this is also cis of theta. Okay. So then now the next question is, why and how is this relevant in linear algebra? Well, there's kind of two things. Matrices can have complex eigen stuff. So eigenvalues, eigenvectors, eigenbases, blah, blah, blah. Eigen stuff, I just don't want to write out all those, okay? And so then really any definitions that we have been working with are the same, or work the same, I should say. There is an exception, so except scalars. Okay, and we'll talk about all that in a little bit. Okay, so this is just a review of complex numbers and how they are some properties that we may end up using today in the videos, and we'll pick up with this in the next video.